Welcome to the Explainer. Today, we're going to pull back the curtain on randomness itself. We're going to find a way to describe it, to measure it, and yeah, to actually understand it. I mean, think about it. From the time it's going to take you to get to work tomorrow, to what you get when you roll a pair of dice, our lives are just full of uncertainty. So how on earth can we describe and work with outcomes that we can't even predict? Well, the key is this really powerful mathematical tool that translates all these unpredictable random events into something we can actually analyze and understand: numbers. All right, so let's dive right in with that foundational tool. This is our first big step in turning all that unpredictability into something we can really get our hands on. In algebra class, a variable like x might have one single answer, right? Like x equals 5. But a random variable, which we usually write with a big capital X, is totally different. It doesn't have just one fixed value. Instead, it represents all the possible numerical outcomes of a chance event, kind of like all the numbers on a single die. Now, here's where it gets really interesting. It turns out that not all randomness is the same. It actually comes in two very distinct types, and, knowing the difference is absolutely key. And it really all boils down to one simple idea. Some random outcomes can be counted, while others have to be measured. So for a discrete variable, we're literally counting whole items. Just think about the number of defective light bulbs in a box. You could have 0 or 1 or 2, all the way up to 50. But you can never, ever have 1.5 defective bulbs, right? There are these clear, separate gaps between all the possible values. But on the other hand, continuous variables are things we have to measure. Take a person's height. It could be 175 centimeters or 175.1 or 175.11, and you could just keep going. There are no gaps at all, just an infinite number of possibilities inside a given range. Okay, so for the rest of this explainer, we're going to zoom in on that discrete type, the countable kind. We're going to explore its rulebook, which is something called a probability distribution. This is basically the secret code. A probability distribution tells us everything we could possibly need to know about a random variable. It lists every single possible outcome, and then it tells us exactly how likely each one of those is to happen. And this brilliant little blueprint, it follows just two simple, unbreakable rules. First, any single probability has to be between 0 and 1. It can't be negative, and it can't be more than 100%. Makes sense. Second, if you add up the probabilities of all the possible outcomes, they have to sum up to exactly 1. I mean, something has to happen. A lot of the time, a probability distribution is just laid out in a really simple table. You'll have one column for the possible outcomes, and the next one shows you the probability for each. It's like a perfect little map of the randomness. We can also visualize that exact same information with a graph, and this just brilliantly illustrates the relative likelihoods. You can see right away that the outcome of 2 is the most likely, just because its bar is the tallest. Simple as that. And this blueprint also lets us find key information almost instantly. So if you look at our distribution here, which outcome is the most likely to happen? Well, the answer is sitting right there in the probability column. We just have to scan down the list for the biggest number, which is pretty clearly 0.38. And this value, the one with the highest probability, it actually has a special name. We call it the mode. So for this distribution, the mode is 2. That means it's the outcome we expect to see more often than any other. But what if you don't have a neat table or a graph? Well, sometimes we can describe all of this with an even more compact and honestly more powerful tool, a function. A probability mass function, or a PMF for short, is kind of like a recipe. You tell it which outcome you're curious about, you plug that number into the function, and it just spits out the exact probability for you. So take a look at this function. This single, really elegant line of math describes an entire probability distribution for a variable that can take on the values 1, 2, 3, or 4. And here's how it works. Say we want to find the probability of getting a 2. We just plug 2 into the formula. 2 squared is 4, plus 1 is 5. So the probability is 5 out of 34. We can do this for every single possible value and literally build the entire distribution table all by ourselves. Pretty cool, right? Okay, so we've decoded the blueprint of discrete randomness. We've looked at tables, we've looked at graphs, we've looked at functions, but what's the big deal? Why is this so important?
Because these ideas give us this incredibly powerful framework. We can take stuff that seems totally unpredictable, as long as it's countable, and translate it into numbers. And from there, we can build a complete blueprint, that probability distribution, that maps out every possibility. And whether we see it as a table, a graph, or a function, it's our key to understanding the hidden structure of chance.
And look, this concept isn't just some abstract theory. It's the gateway to huge fields like game theory, calculating insurance risk, analyzing scientific experiments, and so much more. You now have the fundamental tool to actually start modeling and maybe even predicting the future.